So, okay, good morning, everybody. So, today is our last or previous to last week in the class. So, first, let's cover, like we talked last time, first, let's see or do a very gentle, short introduction to differential geometry of curves this week. And next week, we will be talking about differential geometry of surfaces. I think for someone who works in vision or data science or data engineering, computer science, having this introductory knowledge, these concepts, knowing these concepts is important. I recall during my actual PhD studies, cramming through this book here, Differential Geometry of Curves and Surfaces by Doccarmo. I really recommend it. It's a pure mathematics book. It's fun to look at those different curves and surfaces. Also, because I was working on moving during my PhD, like deforming curves and surfaces over images for segmentation, for tracking, later for medical or anatomical objects modeling. I was really into this. I really thought this is important. I think really it's gonna be a good background knowledge for you too. That's why I thought at the end of this course, the last 1 or 2 weeks, it's a good idea to go over this together. What is our goal when I talk about or when I say differential geometry of curves? I want to be able to represent or mathematically define curves, right? I want to be able to, as the title says, parameterize curves. So for instance, if I ask you, if you, maybe we talked about this before, curves, surfaces, they are manifolds. What is a manifold? Manifold is some structure, geometric structure, which you can model locally as a Euclidean space. So everybody probably first gives this example, or I mean, I was gonna say the Earth. Think of the Earth surface. I mean, it's obviously a 3D volume. I mean, it's embedded in 3D, but it's tangent plane. Or maybe I can show my coffee mug here, the coffee cup. Think of this 3D object, but I can really cover or put patches, tangent planes actually, we will see next time it will be surfaces, to cover this surface. And then actually locally, I am approximating this surface with a 2D plane, a tangent plane. So this is actually a 2D manifold. So locally, it's in a way like a 2D Euclidean space. Similarly, so now I talk to you about this cup, coffee cup. What about a curve? I'm showing you a helix-like curve here, or this is a curve. This is just a wire, my connectors from the tablet to the computer. So this is a curve. And it's actually, these are space curves. It's living in space. Here, this one is living in 3D space. So what is the dimension of this curve, if I ask you? I'm not asking about embedding space. It's embedded in 3D. Of course, I have 2D curves which are embedded in a plane, or I have curves like these in space, 3D space. The embedding space is 3D, right? 3. But what is its intrinsic dimension? How many parameters would I need to parameterize that curve? This is one dimension less than this tangent plane. Locally, you see, let me try to draw it. So look at this curve, just think about this. Can I change the color of this guy? It's black, just 1 second. So I'm tracing this curve, starting from some starting point, let's say here in 3D space. You see it's XYZ, embedding space is XYZ. And do you see my trace? You see it, right? This is an helix. This is, I mean, I now give the hint. I can actually express this curve as a function of a single parameter. And again, unfortunately, the PowerPoint doesn't show this. Maybe I can look at my other screen and try to write this. So this is actually, you see, the parameterization of the helix curve. This is in R3, of course. In R3, so the curve alpha of t is really like this, x of t, y of t, z of t, but how many parameters do I have? It's one, right? So a single parameter starting, for instance, from here, t equals 0, right? And it goes all the way up. It parameterizes my curve. So it's a really 1D manifold. It's the number of parameters with the surface. The locally it was equivalent to a plane. Actually, I would need 2 parameters there. Okay. So is it making sense to you now? Or at least it's a 1D manifold?
Yes.
Yeah. Okay. Yes. Perfect. So, okay. So I think I will have to write the missing equations, but it's fine. So, and just think, for instance, starting from t equals 0, look at this. This is my x of t, y of t, z of t, right? T equals 0, I would start from A here, right? A, 0, 0 points. That's the starting point, right? So T is in, we have to define an interval. So this is a space curve, alpha of T. You see, goes from R to R3. I mean, if it's this is a 3D curve, as in here. Of course, if it's a 2D curve, right, I would have R to R3, but it's actually not the whole R, but it's a range or interval. For instance, I is the 0, 1 interval of the parameter. So it's really actually I to R3 or I to, sorry, R2. But from the real line or an interval on the real, okay? So you see starts from, T starts from A0, 0, then it's like a circle, right? If I didn't have this third dimension, it would be a circle in 2D plane. But also T, as T increases, you see I am really actually going up. So it's really doing this motion as it goes around the circle, it's also going up, right? So this is, I mean, just an example, parameterized curve. So now, oh God, yeah, this is, anyways, this will be all. So these are 2 more examples of curves. Again, I'm showing 2 more examples of curves. T is in, let's say, 0, 1. These are actually 2 different parameterizations of an identical curve. That's the point I'm trying to make. So any curve, so I mean, just maybe think of, we just said, I mean, smooth typically. I can also say it's WT, alpha of T, whatever. Check, it's very easy to plot this. We should normally, we could do this as a Python exercise, but create a vector in an interval and trace these 2. These are, you see this time, I to R2. So X is I to R2. I is the interval, for instance, 0, 1 in R. Okay? So the first one, actually, obviously, what is that curve? Start from T equals 0, starts from 1, 0, right? And traces a circle, right? That one. As T equals 0 to T equals 1, let's say, or it's T to 2 pi probably here, right? T to 2 pi. The range or interval was 0 to 2 pi, sorry. This was my range. Here, we have to really plot this and see this. This guy could, I'm giving this as an example. It could also be landing on here, or it could be an arbitrary curve. I'm just trying to show you, I mean, by picking an interval for the parameter, so define a parameter in R1, okay? And it has a certain range. Of course, it's just sampled, or it's actually lying in some interval in R, and map it to some function of, right? I mean, these are these are vectors, of course, by the way. So these are non-vectors. So these are x of t are just 1D functions, right? You can trace your curve. And so, for instance, here I may be at WT1, here I'm WT2, I mean, and all the way to wherever my latest T's are, Tn, I don't know, maybe this was Wt of 0. Okay. So now we are coming to something else. This is clear, right? Definition of a curve, either a plane or space curve. This is a 3D, a curve embedded in 3D. These are two curves embedded in 2D plane. So here the point this is trying to make is now these two curves, okay, I couldn't draw well, but so this was x of, I mean, these are, by the way, of course, vector functions. X of 0, W0, they are both 1, 0. And it may end up really, I will show you another more obvious example, tracing the same curve, similar curves. But let me see. My point here is, guys, this is, so the first derivative, take the first derivative of the first curve. So they were equal at the starting point, but let's look at their derivatives at that point. The first curve, what is the derivative of the first curve? It is another vector function, minus sine t. I can plot it as a vector, and cosine t, right? So insert t equals 0 there, that would be 0, 1, right? For this guy also you can take the derivative and you can find its first derivative. And it's easy to do it, it's calculus. Its first derivative at 0, t equals 0, is 0, 2. So these two curves may trace similar points, but their derivatives may be different. So here this is trying to make that point different. So actually a defining property, okay, an important characteristic of a curve is the derivative. Actually, we should go for the derivative. So now what is the derivative? So, okay, okay, now this is making, I think, the point much better. This was one curve, 2D curve. This was a second 2D curve. And if I ask you actually what these curves are, I think you guys will say both of them trace a circle, right? So my question to you, actually, I wish I didn't show this picture. What is different between these two curves? That's the question I'm asking you. They are both, I told you already, they are, okay, I already touched it. They both trace a circle, but velocity vector of the second curve is double of the first one. So just, okay, this was alpha, this was beta. So alpha prime t was really minus sine t, cosine t. Beta prime t was 2, right, minus 2 sine t, 2 cosine t. So you see, look at these, this is what we call the tangent, actually, vector to the curve. So for the first one, you see it's the same curve. I mean, they are going through the same curve, but it's the first one has a tangent vector, alpha prime t. The second tangent vector is double the size, beta prime t. Okay, so velocity is different between these. Tangent vector is an important characteristic. I was telling you, we will look at the magnitude of the tangent vector and calculate or write something called the arc length of the curve. That's something important. So let's see. I think, okay, the next slide, okay, we can see it fully. Says, great. We can define arc length. Arc length means I have a curve. Let's say It can be closed, but typically we talk about closed curves. Start at some point here, it's called A, but it could be 0. For instance, I actually want to really measure the length of this arc, okay? Normally, okay, this is, let's say I have a curve. What did I call X? Okay, X of A. If it's a normal parameterization, let's say X was I, normal meaning standard parameterization. Let's say this curve was defined in the interval AB. Okay, this is of course in R. Okay, R, it's just 1D, R. In this case, R3 or R2. I draw it in R2, but maybe make it more general. Okay, so this is, let's say, let's give this parameter a name P. Okay, so X is parameterized by P. XP, okay, it's at this side actually. It's a vector, right? XP is in R3 or R2 as in here, okay? Or another parameter could be like we've seen, T is in 0, 1, okay? So if I, for instance, just trace or traverse this curve, start here, X of A, I'm, let's say, here at some point XP. This XP itself, of course, doesn't tell me the length of the curve. I want to come up with such a arc length definition, and I want to measure actually the tangent, magnitude of the tangent, that's the speed of the curve. So that would be really like doing this approximation, delta x, right? You can think of this, delta x at A, delta x, in this range, right? Between, of course, but at that point, xp, it could be centered. So you could be really, in a way, adding these up. So it's really, for instance, for P, delta x of P. We are trying to come up with something like this to measure the length of the curve, okay? So that would be, then this total thing would be S. Here, then we say, hey, let's go from, okay, let's start again, A to T maybe. T, this point is T, this is A. Now this will be S of T, the length will be S of T. I should say the length. And I can, from this, in a way, this was like, you see, discrete sum, right, with deltas, approximation, of course, but I make it continuous here. And this delta x is actually the derivative, first derivative magnitude, you see. So x prime of P. So x prime is the tangent vector, okay? Tangent vector. And I just integrated with from A to T for all P, so dP, then this really defines, this is the definition of arc length. And this is, if you parameterize your curve, instead of x of P, for instance, now go to a new parameterization, x of S. This is arc length parameterization. It's called independent, this guy is a more intrinsic parameterization, because here my form of the curve depends on different P, right? I can come up with different parameterizations of the same curve. We've seen it, right? With circle, with other types of curves. But with the arc length, actually, it's always wherever I am. For instance, here at this point now, x of S would give me really the length of the, that S gives me the length actually, so it doesn't change. It gives me that parameter is an intrinsic parameter of the curve, so it's really what we call an intrinsic parameterization. Before that, maybe I should go through again the definition. A tangent vector for a parameterized differentiable curve, we assume differentiable. Otherwise, we can't really take this x prime, right? And that is really del x by del P. And it's a vector derivative, right, for each of the components of the curve. So differentiable curve, you see x is I to R3 here. For each t in I, x prime of t. Okay, so for all the curves we study in differential geometry of curves, x prime t is never 0. because otherwise we can't define a tangent vector. So our main assumption is for a regular curve, we expect it to have a tangent vector defined. Okay? So then if this assumption is satisfied, there is a well-defined straight line which contains the point x of t and the vector xt, and that line is tangent line to the curve at xt. I think we all can intuitively imagine this tangent vector, right, on a curve. Okay. Is this somewhat clear?
Yes.
Yes. You haven't seen these anywhere before, right? Yeah, this will, what we're studying will give you a nice base. For instance, after this, you can study Docarmo if you are into this. You can continue with Riemannian geometry later. After the next week, we will be doing 2D surfaces embedded in 3D. Riemannian geometry extends that to Rn. Okay, so n dimensional surfaces in Rn plus 1. So you can imagine that way. Of course, those are all courses on their own. So, I mean, we are really doing a crash course, very rough introduction here. Because it's a 3D course, I believe this is a good base for you. So in some cases, it may be possible to solve for, by the way, guys, if I have a parameterization T of the curve, in some cases, we could solve for T in terms of S, I think T of S, I could say. Then we could really go to parameterization in S. I have an example here. It's a reparameterization of a helix. Actually, next week we will write much more, but I want to maybe write one page about arc length parameterization. Just a side example maybe on this thing. So we defined S of t, the arc length, between A to T. Okay, so maybe A to T, X prime. So guys, I mean, when I talked of the curve about, I mean, mentioned the curve X, it's a vector function. Sometimes it's a misnomer, I know, but you know, X of T, the first coordinates vector, I mean, the function is also X of T, don't get confused, okay, this and this, scalar and vector. So X prime, the tangent vector, its magnitude, right, dp, this is my arc length, so let's say arc length. So let's maybe draw a picture again of a curve embedded in 3D. If I have maybe, I mean, it could be any curve. The reason I'm doing that fold is to show it's really twisting in 3D, and we'll talk about twisting soon. So maybe the starting point, if it starts from A, this is my X of A in 3D space, okay? The parameter is equal to A here, P is equal to A. So here is, let's say, P is equal to T, okay? That's the vector, the X of T, okay? And we were talking about length of this curve, right? Length of this section, S of T. That's what we define. Also, using the fundamental theorem of calculus, first fundamental theorem, maybe using, I think this is all well known to you. The derivative relates to the derivative using first fundamental theorem of calculus. I can take the derivative of this guy, ds by dt, and I know it will be actually x prime t, right? I mean, in this way, the magnitude x prime t. This is so showing me the arc length parameter, take its derivative, it gives you the speed of the curve with that parameterization. So, for instance, e.g., my example to you, let's reparameterize a helix. Reparameterize a helix curve. Remember, we said a helix was For instance, let's say unit circle like helix, sine t, t, okay? This is, let's reparameterize with respect to arc length. You can do these things, okay? So I can, so the helix is actually in this way. Maybe I could again draw it here. So start from maybe some t equals 0, and just look here, from t equals 0, it would start from 1, 0, 0 point, right? X, Y, Z. And it would do something like this, right? This is an helix curve. Continue until, don't know, where the parameter ends. And let's take the derivative. X prime t is minus sine t cosine t 1. Now let's look at the speed of this curve. So you see t was here an arbitrary parameterization. We're trying to go to this arc length parameterization, intrinsic parameterization. So this is really sine square t cosine square t plus 1. Actually, it's really square root 2. In some cases, it's really possible to do it this easy, that directly. And now, because I know my s of t, remember s, the arc length was a 0 to t. Let's say t was in 0, 1. Let's write our arc length formulation. It's the integral until some arbitrary t, right? Because I'm trying to measure arc length of the curve until that point t. So here, maybe let's say t was here, t equals 0, t equals t here, and we go up there. Actually, maybe I should use another parameter here, p, because I said this is t, so this is p equals t, right? I mean, a specific point t. Because the reason is I need a dummy variable, right, in the integral. That's why I went to another parameter. This is p here is a dummy variable. So now 0 to t square root 2 dp. This is really square root 2 t. So from here, t is really s over square root 2. I need to just reparameterize, guys. Reparameterize meaning insert, of course. Now this is calculus. X of t of s here. Of t of s, and in the end this will become, of course, x of s. I mean, we are getting rid of t parameter there, right? So it's really cosine s over square root 2 sine s over square root 2. So this would be the curve parameterized by the helix curve, parameterized by arc length, right? So let me see if I have another example or no. Okay, yeah, the point here is this. This is a good point. I should really mention this. That's why I checked my notes. Here, the difference is, for instance, x of t, x of 0, x of t. Let's say t was equal to something like 1, t was 1 or 2, I maybe here t was going even further, I mean t 0 to a some other number, t equals 2, let's say. So x of 2, this was x of 0, okay. So x of 2 at this point was telling me just the curve, right, values when I inserted t equals 2 there. I mean, that's just an arbitrary parameterization, okay? So some people interpret that as time. So it's like my curve value at time equals t. Time is just a parameter, right? Notation or name for a parameter. But with the arc length parameterization, if I say, so the difference between t equals to and s is equal to, it tells me actually when I have x of s equals to, right, with this parameterization, I know now if maybe I'm somewhere else, but if I was here, okay, let's say I was here, I know now I'm 2 units away from the starting point of the curve. So that is the difference. The other one was just some arbitrary naming, we said time equals to, okay? So this is where we are This tells us where we are on the curve after we walked 2 units. I mean, I'm trying to emphasize the difference between an arbitrary parameterization of a 2D curve or 3D curve or arc length parameterization. That's the thing. After we walk 2 units along the curve or on the curve, I mean, it's the same, right? On the curve, let's just fit it here. That's my point in this slide, actually. Is this clear? The arc length, let's say arc length parameterization versus an arbitrary parameterization. It's an arbitrary parameter like the T, P, it makes a difference. Okay? Okay, I think your brain probably has already warmed up to the idea of space curves, 2D or 3D curves, how they get parameterized. Now let's go back. Let me open also my slides here so that we could, okay, let me see. I think we were here, we done. Okay, we are done with this. I hope it's clear, arc length is clear. Right, please ask if something is not clear. Okay, let's start. So we said, this is unit, by the way, we define tangent vector. We can always normalize it, right, with the magnitude of the tangent vector. Of course, for an arc length parameterization, already this would be it, right? Because I know this would be 1. I should probably derive that somewhere. But let's see, let's continue. This guy will automatically be itself. So let me, notes are all done. So let's leave it up here for now. My point here is to define, let's say I have a curve x of t, you see shown here. I have the tangent vector t of t. An important thing again, just please remember, there should exist a tangent vector. So we should always say at any point for all t, x prime of t is never the 0 vector. Okay, I should always have a tangent or the derivative of the curve. Okay, and when there is the singularity exists, it's called a singular point of the curve when x prime of t is 0, and then that's not a regular curve. Typically, we study regular curves. Okay, that's the point here, regular curve. Okay, so now, okay, nice. Trying to see if I'm missing any other things. So guys, now we define tangent. We will define another important vector, okay? And that comes through this. If I have my tangent vector and its unit tangent, take its dot product with itself, it's equal to 1. I typically motivate it in this way. Now derive this, take the derivative of this equation. So that would be 2 times, right? T dot T prime dot T. I mean, these are, that's equal to 0. This doesn't matter. Dot or inner product, right? I mean, I'm using it equivalently. This is also the same thing. Now, I'm seeing that this equation tells me T prime is orthogonal to T. So I'm seeing actually my normal vector is proportional to T prime, which is really nice, right? I derived the curve itself, x prime, it gave me the tangent vector. Now take another derivative on the tangent vector. So n of t normal is, you see, second derivative. It's proportional to the second derivative of the curve. Okay? And it's these two, we will also add a third vector later. Currently, these two, tangent and normal, you see, form a nice orthogonal basis. For 2D curves, this is enough, actually. Okay? Now the third one comes, exactly. This is a this is called binormal. Okay, let me write, these are just equals, right? Okay. And let's we form a plane from n and t, normal and the tangent. That they two vectors, right? In a, they form a plane, n and t form a plane. Now we take the cross product and form the normal to that plane, which is my b vector. You see, this will be normal to that plane. This plane is called the oscillating plane of the curve. So you see b of t is the normal or binormal actually. That's why it's called binormal to the oscillating plane. So let me see. I think here, okay, the important thing, one of the things we will be again studying will be length of the binormal curve. Okay, it's coming up, and it's gonna also tells us how quickly the curve is pulling itself away from the oscillating curve. Actually, we will also talk about curvature soon, and we will talk about something called twisting or torsion of the curve. They will all relate to the speed of this binormal and the normal, actually, unit normal, how quickly they change. Okay, so their derivatives. So this is cool. This is probably again something you guys heard for the first time. And these, by the way, three vectors, tangent, normal, binormal, they form something called a frame. You see, any curve, bring any 3D curve. I can define these three vectors, tangent, it's normal in the same plane, and a binormal with the cross product of the two, right? Probably here the normal would be like this, the tangent is like this, and binormal would be coming, for instance, out of the plane. Okay? This is something you should really know when people talk about frame of a curve. It's formed by these three important vectors. Now you define a curve actually. Okay? Okay. Let's continue with the frame. Guys, t, we set tangent, we defined as the x prime, right? The first depends on the first derivative vector of the curve, just normalized by speed of the curve. Normal is now, remember, it's proportional to t prime, and again we make it unit normal by normalizing by the magnitude of the tangent. Now b of t is the cross product of t of t, n of t. Exactly, it provides an orthogonal frame anywhere on the curve, and all these dot products are zero. Because, I mean, they are all orthogonal to each other, right? So that's the point of frame. Oh, I mean, these are, yes, of course, these are trivial. And we already derived, every time I go to the next slide, it deletes what I'm writing. So sorry for that. And remember, we already derived this. Now I'm thinking I was deriving this here. Okay, it's good. It will be in your notes actually. So sorry, I should be going. It's going to this in the end. It's saying t dot t is 1, t prime dot t plus t dot t prime is 0. This is what I showed you a few slides ago. From here, you can see that t and t prime, which is normal, they are orthogonal, of course. Okay, this is good. And I think that's the last thing it's writing here. This is the t prime dot, I mean t dot n is 0. Okay, now frame should be fine. These three vectors, I think you guys probably understood it. Another important concept is curvature, to define a curve. Typically, the notation is kappa of S, and it is actually proportional to the second derivative of the curve. If it's arc length parameterized, it's just alpha prime of S. Measure of how rapidly the curve pulls away from the tangent line. So this is really a nice example from the Carnot. Imagine I mean, it's already here actually. This is some curve. Imagine looking at these tangents here. Actually, it's the second derivative. These are the first derivative. So we are looking at how quickly the first derivative changes, right? I mean, and also normal or normal changes. I mean, it's similar, but the tangent here, it's actually on the tangent because alpha prime is the tangent vector, then alpha double prime is how quickly, right? I mean, it's derivative. It tells us how much it changes. So look at this curve, compare it to this one, and look at the tangent vectors here. Here, these were more smoothly changing. Here, you know, from this point to this point, look at the tangents. Very quick changes, right? So alpha prime would be smaller here, but the alpha double prime, I mean, would be much larger, right? Compare these two. And this is somewhere in between. And you can tell, right, actually from here, it's, I mean, close to, for instance, a line, straight line. What is the curvature? Is this tangent vector changing? No, right? This curvature is zero, line, straight line. So closer to straight line, curvature is really small, but very quickly changing curve. All these quick movements, things like that, right? These are very high curvature locations. I mean, these curves have high curvature. So we said curvature is a measure of how much the curve bends actually. Exactly, right? This is bending. How much it bends, maybe a little bit less and things like that. So now let's look at, okay, you can't see anything. I have to look at this, right? These special characters are not there. This is trying to say now, actually we tied it to the derivative of the tangent vector, right? Kappa is the magnitude of derivative of the tangent vector. Okay? Now this slide says, it's a little bit more busy slide. This was in terms of the arc length parameterization, guys. Now this is another arbitrary parameterization, t prime t, okay? It's equal to del t by del s and del s by del t. And remember, we've seen this del s by del t is equal to, really remember that integral arc length, just single. And the speed of the first derivative or magnitude of the tangent, right? X prime. So from here, actually, you can see t prime, t magnitude is equal to curvature, which is this guy, curvature times x prime t. So curvature is for an arbitrary parameterization of the curve. You have to normalize by the magnitude of the tangent, okay? That's what this slide is saying. So, I mean, if it's arc length parameter, that's the importance also of arc length parameterization. If it's really arc length parameterized, you see it's itself, but with an arbitrary parameterization, curvature is defined in this way. But important thing, maybe forget about all these derivations. You see, curvature is proportional to the t prime, right? That's the point, actually. If you forgot this, recall s of t was 0 to t x prime t. Okay, p dp. Go to a dummy variable, right? I need to go to a dummy variable. Okay, I mean, don't get lost in the equations if you couldn't follow, but actually it's not difficult. But still, curvature is a measure of how much the curve bends. Okay? I think we've already done these. These were the same, guys. So, this is something. Okay. I mean, we've already defined it, but you can open this up, derive this. X prime cross product with X double prime, and in the denominator, it's X prime T cube. This last step requires derivation. Now I recall I have this derivation somewhere in my notes from before, but I don't have it with me. If you are interested, let me know. I can upload that derivation to Ninova too. But you can go from here to here actually, now with your current knowledge. Okay? Start from definition of t, continue with deriving to get t prime of t. And if you are interested, I mean, the point of this is if you had x of t defined, you can have a, you see, closed form formula. If you have a parameterized curve, you can calculate x prime t, x double prime t, and of course these cross products and magnitudes. In the denominator, I have x prime t, which is the speed of the curve in the magnitude, right? Q, and I can have a way to calculate curvature or kappa at each, of course, parameterization point. I mean, probably we have quantization, right? When we numerically implement this. I mean, t is, let's say, between a to b, it could be 0 to 1. And I am really calculating kappa at each of these points. Okay? Through this expression. This is also a very well-known expression you can find in differential geometry texts. So that's why I wanted to show it to you. Like I said, if you are curious about the derivation, let me know. You can try yourself. Still, I think it was a little bit involved, maybe full page or 1.5 page derivation. I can define something called inverse of the curvature. And this is called radius of curvature. This is a very intuitive thing. So think of, guys, I think best example is a large circle. Okay, or a curve that can have maybe a curvature like this. But you can always fit a circle there actually. That's why it's called circle of radius. R has radius of curvature R. Okay, so let's say I have a circle of radius R and it has curvature R. Radius of curvature, inverse of the curvature. Actually, I think it should be inverse. Now I wanted to talk about a large circle. What would be if you were walking here? If it's a very large circle, I mean, just maybe think of, or it could be a sphere of Earth, like, or maybe very, very large, still talk about, let's say, just circle now, 1D manifold, don't go to Earth. The curvature you're feeling here, the bending, right, amount of bending, would it be large or small? So large R, we already said R is inversely proportional to kappa, the curvature. This is small curvature, right? And it's obvious actually. So now think of, I mean, obvious meaning compare walking on a large circle to small circle. Look at the tangent here, how the tangent changes. It was slowly changing, right? Slowly changing t. Now look at a small circle here. Okay, it's all gone. Anyways, small circle, a small circle here. It would be a large curvature, right? R small, kappa large. Okay, I think I just jumped, but anyways, that was the point here. Small circle. So similarly, actually, compare these two. I can fit a circle here And I can actually fit a large circle, a small circle, a large circle here. So this R, you see, is inversely proportional to kappa, the curvature. Okay, this is called radius of curvature. Now I think we also define in the next slide kappa to be something curvature as a sine. Actually, we can also define it in a sine way, sine form. Look at this curve now. The curve here, when you plot the tangent and the normal, look at the tangent and the normal. These guys are both on one side of the curve. Okay, I'm going from here, and my normal and tangent are on the other side. Okay, or just stay on one side. This is the case for kappa negative, and this is a concave part of this curve. Remember your concave, convex definitions, concepts. Here actually it comes from also kappa, sine curvature. When I have a negative curvature, it's the concave part of the curve. Now look at this part, guys. Draw the tangent and look at the normal. Okay, with the same convention, it was T to N, right-hand rule, and now N points inside the curve. For instance, here it was pointing in the first one outside. So now this is a convex part of the curve. Kappa is positive. Okay, curvature is positive. Here, curvature was negative. Curvature is negative. Okay. I think probably you recall this somehow, convex, concave, and relation to curvature or the second derivative, right? We look at the second derivative of functions. Fine. So we defined parameterization of a curve. We defined the tangent curve, normal curve, binormal, tangent vector, normal vector, and binormal vector. That's a frame, right? The curvature. So these, as you've seen, all depend on derivatives of the curve, right? That's why we want a differentiable curve, smooth curve, where the derivative is not zero, so that the tangent can be defined. So you can see tangent is the probably first of all the first important vector, and then how quickly it changes we look at, or it gives us actually the curvature or bending amount of the curve, right? So that was the curvature. So now we go to some other concept, torsion. This is how much the curve twists, or twists is actually, again, I always show it with some wire that is around. So if I have a curve like this, in a 2D plane, you can think of it as a 2D planar curve, but if I start twisting it in 3D, you see, think of an helix, right? It has a lot of torsion. So if you start twisting a curve like this, now I'm increasing the torsion of the curve. If I want to measure that, I want to look at the binormal vector. Okay, so the tau, it's the torsion. Let's say it's symbol is tau. It's defined as the magnitude of the binormal's derivative, meaning actually how quickly binormal changes, how it twists actually in a way, right? So a binormal is, remember, the normal vector of the oscillating plane. Again, then how fast that oscillating plane, this n and t's plane changes, right? This is, remember, this guy is normal to that plane. It makes sense, right? So if it was a planar curve, I have a plane and t-plane here. Now start twisting the curve, that plane quickly starts, right? I mean, starts changing very quickly. That's the idea of torsion or twisting. So that's why I'm trying to move to the next slide. Let me just go to the next slide, maybe. Yeah, we've defined this oscillating plane. Uh, exactly the plane defined by the vectors tangent and normal vectors, and the curve locally resides in this plane. This green plane nicely shows actually that oscillating plane. And B prime measures the rate of change of neighboring oscillating planes. Exactly, I was saying this in the previous slide, actually, how fast those planes change once you start twisting this, right? Just imagine those, maybe probably I should bring some planes, but you see, if you start changing this oscillating plane also, if you start twisting the curve, this oscillating plane also changes, start changing very quickly and rapidly. Okay, and how rapidly also the curve pulls away from that oscillating plane. This describes torsion of the curve. The equations, we've already defined the torsion as B prime, the magnitude of the binormal prime. And I think here is another helix-like curve you can see with a lot of twist here, right? And look at how this frame T and B changes, right? That also very quickly changes here with the B also quickly changing. So in terms of the curve C, its derivatives, okay, you can also derive a expression. This is derived in the Carmo. If you guys want to look at the details, now you see we're looking at the third derivative of the curve. C is now, guys, I mean, C of P. I mean, let's say this was defined as C of P. P is the parameter, or T, it was T here. Okay, T. Okay, T, right? I don't know, maybe T was 0, but don't mix this T with tangent. Here, the tangent vector was also T. Anyways, uh, T of T, let's say, still, okay. T is, remember, from an interval in R, I don't know, maybe an AB, a real interval to, in this case, R3, right? Which is C of P, a vector in R3. And I can take its derivatives. These guys will be also vectors, of course, right? Because C itself is a vector function. Okay, so that's why I can take cross products, dot products, and things like that. Okay. Also, in the end, guys, you when you have now, we've looked at, defined these tangents, normal, binormal. In the end, we also, you see, started calculating their derivatives, tangent derivative, the normal derivative, and binormal derivative. Okay, I have to again complete these guys. Now, Frene equations actually tie all these together. So you have tangent T of S. Okay, they are here parameterized by arc length. Normal vector N of S, binormal vector B of S. Okay, and the derivative vectors T prime, N prime, B prime. Okay, and we define curvature. You see, we also have curvature and torsion here. Okay, curvature and torsion. So we have all these kappa, tau. We have the vectors T and B. Something is wrong. Okay, all right. And binormal. And now we also have their derivative vectors up. Prime. So we relate by using all these vectors and scalars actually, right? Kappa and tau, the torsion and curvature are scalar, the others are vectors. You see, they all define the curve actually. This is a curve is shown at the bottom here, x of t. It's the curve, and actually the or x of s if it's parameterized by arc length. you can look at the derivations of these. Indocarmo, this must be Indocarmo. But this is the famous set of Frene equations that define the local geometry of the curve and all the relations between, you see, these different quantities or entities that locally define a curve. Later, it's coming up, we will have a fundamental theorem of curves. I'm trying to remember the name of the uh, theorem of curves, fundamental theorem of local theory of curves. Okay, it's coming up 2 slides later. That will talk about actually with these parameters to be able to uniquely define a curve, almost uniquely actually. We will see that. Okay, so now Frene frame physically says take a straight line in R3. Let's say if this was a straight line, I don't know if you can see this. Bend it. If you start bending it, you obtain curvature. You can, of course, locally bend it in different ways, right? I can do convex, concave, different sections. I hope you can see this. This is bending and you obtain curvature, different curvature along the curve now. Now, this was just curvature. Start twisting also in 3D, right? You see, start twisting this thing and you start having torsion also. So you introduce also very much varying binormal vectors. With bending, your normal vector starts to change. With a straight line, curvature is 0, right? Torsion is 0. Normal vector is constant. Tangent vector is constant. Nothing changes, right? With a straight line. You introduce these bending and twisting. So that is curvature and torsion and all those varying tangent, normal, and binormal vectors, you start to obtain different arbitrary curves. Okay, so we're trying to characterize curves. You see, and Frene frame really helps us do that. And this is the biggest theorem in the differential geometry of curves, fundamental theorem. So it says given differentiable functions, I'm trying to see, I think everything is seeable here. Okay, see. Differentiable functions, kappa and tau. Kappa is the curvature, tau is the torsion, S is the parameter here. It's arc length probably, or could be arbitrary. S is the arc length, okay, I see it in the definition of the theorem. There exists a regular, remember a regular curve is when tangent is not 0. Regular parameterized curve C from that interval, arc length is also between 0 to total length of the curve actually. So that I to R3, okay, we define C. This is definition of the curve function. See, kappa S is the curvature, tau S is the torsion of the curve. So this says, give me a kappa curvature and tau. That means actually, I mean torsion and curvature. That means I already defined tangent, normal, and binormal because to calculate these, right? I need them. And now I can, depending on all these curvature and torsion at each point of that parameterized curve, I can define or find a regular parameterized curve. So it uniquely identifies, but just with up to a rigid motion. Any other curve satisfying the same conditions, meaning the same curvature, same torsion along the curve. It's the same curve, but it may be rotated, rigid motion. It's in R3, so 6 degrees of freedom, right? We've studied rigid motion group in this course, SO3 plus translation. Remember SE3, special Euclidean group. So it means just rotate in 3D this curve, right? You can somehow we rotate it rigidly. I'm not changing, deforming, and translate it. it actually can have the same curvature and torsion. It's almost the same curve. I mean, up to a rigid motion. Not almost. It's the same curve up to a rigid motion. This is a important theorem of the differential geometry of curves. So curvature and torsion actually define a curve up to rigid motion, uniquely define a curve. Okay, if you have kappa of S and tau of S for all S, of course, in the interval, right? So what are some uses? I'm also here, the important thing is if I'm calculating or given kappa and torsion, I know the Frene frame, right? I should have the Frene frame. So uses of Frene frame, I mean, I can get corresponding Frene frames of the kappa and torsion, curvature and torsion. So I remember I tried to find in the past some work that use Frene frames. First of all, the main use is in computer graphics field. Given a trajectory of an agent, an object, this Frene frame is important because you trace the trajectory, right, through knowing this actually tangent, normal, and binormal vectors. You are along, it's a trajectory curve, right? You are moving some agent or some figure, something, some object. So in computer graphics, Frene frames are something known and defined. Okay, that's something. So animation, I mean, field, we could say probably, right? Because you want to move an object along a trajectory. That's one use. We also have another use, skinning a surface along, again, a path. Path and trajectory is important. So give me a path. I could start maybe placing spheres, skinning a surface is like this, and then actually I can create a surface along that path. For instance, this is called skinning a surface. So from a 3D trajectory, a curve, I'm creating a surface. For instance, to do that also, I need to define my Frene frame, this 3D orthogonal axis, right? T, N, and B. On the right, there is an interesting application, an old paper, but it was using actually medical imaging and vision, trying to study 3D geometric properties of 3D spine curve. You see spine, your spine curve, you can see it here, your spine, it should obey at least or be within some range of some geometric positioning, right? I mean, if it bends too much or doesn't bend too much, there are problems. So for instance, thoracic scoliosis, I think this was too much bending or abnormal bending. So for instance, here is a normal spine, and this curve can be extracted. For instance, let's say you want to come up with an algorithm to study this scoliosis. You may take X-ray or CT of this patient, actually it's computed tomography, or it could be any other modality, medical imaging modality, and you can extract these vertebrae and the center line of that vertebra to get this spine, 3D spine curve, as shown here. Look at this. And at each point, I mean, you can parameterize this curve, and at each point get this Frene frame, orthogonal basis. And that will help you analyze the curvature, torsion, right, of the curve. For instance, on the right, there is an abnormal patient's abnormal spine curve. And to be able to study or analyze the difference between these two, you should know how to analyze curves, right? How to define geometry of the curves. I think this is a very good example of the uses of what we've seen until here from this morning, because I believe some of you may have been asking, okay, we've learned about these differential geometry of curves, so what? I think these examples in this slide is, I hope, giving you nice intuition or uses and applications of this differential geometry of curves. Other thing is, for instance, for geometric recognition of curves, I can look at, for instance, as features, actually extra features. For instance, to define a curve, we can, maybe this is a curve. In the past, we worked on these things actually. Look at total curvature. Were we? Yes, we should also. So it's total curvature. My notes, I saw it. So curvature from A to B, wherever I'm going. Let's say A. Start from A. I traverse the curve to B. Okay, A to B. Let's say it's a closed curve. A to B. Kappa squared ds. Let's say it was parameterized by Argman. So I can take this as some feature, global feature, actually. So maybe I should say global feature of curves. So this is another item, I mean, global features of curves. For instance, total curvature. Now, to calculate such a feature, you need to know what curvature means. Okay, you can now calculate, for instance, total curvature of a curve, meaning calculate curvature along the curve and sum it up. Okay, and square it and sum it up. Another one. Okay, before uses, actually, let me say this. This is, remember, already something that is required for a regular curve. Remember, we already said we don't want this. We assume, I mean, this is the definition of a regular curve. Tangent vector never becomes zero. Okay? Actually, no, tangent vector never becomes zero. So C prime is not zero, right? I mean, this is equal to T. T should not be zero. This was for a regular curve. Now, T prime of T, when it becomes zero, this is something else. This is also not wanted, right? Because for Frene frame, remember, we also want T prime of T. Okay, so that's also something that makes our analysis undefined. T prime of T zero, that's where the second derivative of the curve is zero. So actually second derivative changes sign, right? When it's zero, it goes from negative to positive or positive to negative. So these are called inflection points. What are the other equations here? T is this guy. We know normal, you see, then I can't, if T prime zero, normal can't be defined. That's a problem. And then binormal was, is not definable. I mean, I can't define the binormal if I can't define the normal. Okay? So you see, this would not be enough. For a regular curve, we said T never becomes zero, but I also want T prime of T not zero. Okay? All right, so what else? I was saying some global features of curves. Now you guys can define. This is another global feature or property of plane curve. Of all simple closed curves, these are some important well-known differential geometric concepts. So it says, of all simple closed curves, simple curve means it doesn't have an intersection on its own. I mean, this is not a simple curve. Simple curves don't have, I mean, it may be like this, but it doesn't cross itself. This is not a simple curve. In plane, I mean, in the plane. Of course, in 3D, that 8 could be just a twisting and it's not going over itself, but it's still a simple curve. Now, this is saying I have curves like this, let's say with a given length L, I may have a curve like more, you know, simple looking like curve. The question is which one bounds the largest area? This is was studied in differential geometry for some time. This is called isoperimetric inequality theorem. A is the area of the region bounded by C, A, and L is the length of the curve. Okay. Square the length. When it's equal to 4 pi times the area, this is a circle. And this is the most compact shape you can find. Actual circle is an amazing figure or shape. Guys, it's a shape you see which satisfies, I think we have for all others, this is greater equal for all other curves, right? This L square is always larger or equal for pi a, but for only circles, for circle only, we have this isoperimetric inequality. Now you may be asking, hey, why am I talking about this? This is another feature, for instance, about the blobiness or circleness, circularity index. So you could look at these L squared and A and look at this relation. If it's close to this equality, it's a more circular shape if you can calculate the area and the length of the curve. If it's getting larger and larger, the length is much, much larger. Maybe for something, you know, the length gets large, but you see area is not that large. You see this would be a very non-compact shape, right? Compare these two. Here L square is much, much larger than 4 pi a. So this is a compactness feature. You can think of L square over A, 4 pi a, for instance. I hope you see what I'm saying. We're talking about some features of curves now, or features that could define, characterize curves. Of course, now in this learning era, like deep learning era, I hope you are not in a mood like, hey, I would let the neural network look at these. No, you should really know, for instance, if you are designing a model for recognition of shapes or curves, these things could come in handy. I mean, you should know what these things mean too. You should, in order to also explain, right? For explainability, interpretation, these things should be also in your mathematical toolbox. This is, I just write this because it's also a very interesting theorem. This is the last theorem I think I'm giving you for the curves, differential geometry of curves. Very famous theorem, Jordan curve theorem. I recall again during my PhD times, because I was really interested myself, actually, it was an extra interest in differential geometry, studying Locarno, was looking at this theorem. I think it had like maybe 100 pages of proof, but what it says is very simple. Just have a simple curve, closed curve C. It says it will divide the plane into two, which is one of them is the interior of the curve, the other is the exterior of the curve, and C constitutes the border of those two regions. I mean, this seems very obvious to you, but for mathematicians, they went through a lot of trouble to prove this theorem. Okay, the interior and exterior, like a simple curve dividing or partitioning the space into two. I think this was very interesting to me, very difficult theorem to prove. This is called Jordan curve theorem. And we actually use, of course, interior and exterior of curves. This is an important concept too in analyzing, again, regions, geometries, curves. For instance, I think with the Jordan curve theorem, trying to partition a space into interior and exterior of a curve, when you are just given the curve, I recall myself writing a code for extending rays from, for instance, here, extend rays. And if, for instance, the curve, ray intersects the curve 2 times, I am inside the curve. And if my ray intersects the curve more than that was it, right? I should not, I'm trying to recall this. Should I start from, I should start on the curve, sorry. On the curve. Extend, okay, here. Extend a ray, let's say horizontal rays on both sides. I mean, this was wrong. Start on the curve. I think if it intersects the, let me see, curve 2 times, I am at the exterior. If it intersects the curve odd times, I am inside the curve. So I should really probably intersect the curve on the ray one on one side. I'm trying to recall this. Have any of you, my question is, have any of you worked with such geometric objects? Because during my PhD, I was working on polygonal curves, active contours, laying contours or curves or surfaces on images and trying to deform them to be able to do the segmentation. So I needed to really know, for instance, when I am inside, when I am outside the curve. So I needed these tools, actually, differential geometric tools, to be able to say this. So do I have a note for this? I'm trying to think. So let's think. Here I would intersect it 2 times. I'm trying to see interior, exterior. Maybe I should really start somewhere here. If it's extending to one side only. Yeah, actually it works. Now I'm seeing it works when I extend the ray on one side. Even times I'm exterior, odd times I'm interior, actually. Because if I'm here and it doesn't intersect, that is 0 even time. I'm exterior. If I'm inside, it should intersect the curve odd times. So I will think of such an example now. You may ask, hey, what about this one? 1, 2, 3. Yes, I'm inside. Odd times is correct. Do you guys see what I'm doing? Okay. I mean, how to find whether I'm interior or exterior of the curve. That's an algorithm I was trying to think of. And I think now it works. If I start outside, okay, even times the intersection. Anyways, I mean, these things were really useful for actual implementations, for working with these curves, coming up with features. You see, in this, with the help of this theorem, we can come up with regions, right? We define start defining regions inside and outside the curve. Okay. How is it going for you? I mean, this is okay. It's the end. This was the last slide. So these, you see, we've seen several properties. We've defined Frene frame. We've defined all those tangent, normal, binormal, vectors, important vectors to define a curve locally. Frene frame is locally changing around the curve. Remember, of course, it's it's something here, it's something else here, right? And then we define curvature and torsion, two scalar quantities, of course, which change along a curve. We define arc length, which is important. Then we defined some global properties, right? And uses of Frene frame. Torsion we've defined already. This isoparametric ratio, for instance, lengths and areas of curves. regions of inside and outside curves. And this is actually a very crash course in differential geometry of curves for you. I believe I really probably touch on most of the important notions in differential geometry of curves. My advice to you would be will share these slides, look at these slides, and for extra things, or if you are interested, just start looking at first few chapters of the Carmon. Those are for curves, and then later chapters of that book is for surfaces. So next week we can look at differential geometry of surfaces. Any questions until here from the curves, differential geometry of curves? Questions or comments? Let me see. Yes, fundamental theorem of the curves, you guys know. Frene equations and Frene frames. I hope intuitively bending and twisting are okay for you. Just remember them at least, I think, when talking about curve properties. Okay? So let's do a recap first, and then just a sec. Let me look at my notes just to make sure I have everything here. So last time, right, we had looked at differential geometry of curves. Again, of course, I'm saying these are just some quick introduction, but I think still it gives you a good idea about what these structures, geometric structures are. So I have a curve. It could be in 2D or 3D, right? Embedded in 2D or 3D, but you guys now know it's a one-dimensional manifold. This is a 1D manifold, meaning I have one parameter that really parameterizes this curve. So it's like start, for instance, some p equals 0, p1, I mean, some, of course, I will say p2, but of course, I'm not sampling here. So another p, I mean, like it's like a time variable, right? As time passes. So for instance, it may be, so don't say p, it may be actually closing for a closed curve. So it's p in this interval, 0, 1 interval. So my C of P, let's say, right, was actually an embedding from this interval. This was I in R. So actually the definition of C mathematically is from I to the embedding space. It could be R2 or R3, right? A space curve, 3D space curve. But it's a 1D structure actually. Or if it's a 2D planar curve, of course, 2D curve. R2 goes to R2. So XP, if it's a 3D space curve, of course, I have my mapping to this vector, right? 3D vector, remember. And one important structure or element, geometric entity we talk about, remember, is the tangent vector, right? We did this last time, so I have a P here. Here, what is important for me is, remember, for a regular curve, so this guy is C prime P, or del C by del P. This is tangent vector to the curve at a point. Of course, it changes at a point P. It changes at each point on the curve. Remember, this is an important actually property or geometric entity for us. And remember, for a regular curve, we want to be able to define this thing. So we say C prime of P is not 0. It's not a 0 vector. I want a tangent vector to be defined, i.e. tangent vector should be defined. for a regular curve, right? Otherwise, we can't define any of the geometric entities. Then the second thing was, remember, okay, if let's say this was my t, then we call, okay, maybe let me be just maybe under, let's say vectors are denoted by under bar t. This is t. The second or the other important geometric entity, of course, is the normal. Of course, this is also defined in 3D. I'm showing in 2D, but remember, this is then the normal, which is actually orthogonal to the tangent in that plane, right? And then, okay, so let's say normal was normal vector. And then we defined something called arc length. First, let me define arc length. This was a independent or intrinsic parameterization. And it would be like if I start from s equals 0, when I go to a specific s, actually that guy is equal to really length, arc length of the curve. That's why it's like an intrinsic parameterization. So I can define it in terms of other parameters. For instance, 0 to p or t, let's say, if it's s of t, just to use a dummy variable. Or I can keep p and then use t as the dummy variable. Okay, s of p, let's say, is then 0 to t. Now I need to define, remember this c prime was also important because it gives me this tangent vector, the speed of the curve, right? So it's a really like telling me how fast I am moving along the curve, right? That parameterization actually is moving along the curve. C prime of t, the magnitude you see of the tangent vector dt. This was my arc length we did last time. And then we said arc length S gives us an arc length parameterization. Now, for instance, I can talk about n of s, or also t of s. I can talk about, let's say I parameterized my curve with arc length, n of s. Remember, this was actually the equal to derivative of the tangent vector, because derivative x was derivative of the tangent was normal to itself. And then actually when I take now another derivative on the tangent, remember tangent itself was derivative of the curve c of p, curve function, right? Now its normal vector is actually proportional to second derivative, right? So it's really uh, telling me normal is looking at how fast the tangent changes, and the tangent was looking at how fast the curve was actually, the curve function, parametric function was changing. Then what else did we say? I mean, this is clear, I hope. Remember, we started this by from the inner product, setting it to unit tangent, let's say, and then taking derivative t prime dot t, it's equal to 0, and then we said, hey, this should be the normal. This was the way we did this last time. What else? This was normal to the curve. So what else was there? The third important vector was the binormal, remember? And that is defined by B of S is tangent cross producted with, so it's normal to both of them, right? The normal. Why was this binormal now important? This is important for 3D space curves. So 3D space curves embedded in 3D. This is important because it lets us also define a local frame, coordinate frame, 3D in 3D, Frene frame, remember, Frene, local Frene frame for a curve. It consists of T of S, N of S, and B of S, these three guys. So B now comes out of the plane here. Let's say, let's say it's something here, B of S, like this. And we have, for instance, T and B, okay? Local coordinate frame. And here, important thing to properties of the curve. Remember from the fundamental theorem of local curves in differential geometry, the curvature was, we should talk about curvature here. Curvature was how much, telling us how much the curve bends. So maybe let's do that here. Curvature of the curve. Remember, this is, for instance, a high curvature, right? And this was proportional to the second derivative of the curve. This tells us how much the curve bends. So these are, you see, characteristics of a curve. This is high curvature. This is low curvature, right? Low curvature. And actually also depends on the speed, you see, or the rate of change of the normal vector, because normal vector was also proportional to actually t prime s, which is of course proportional to double c prime. And curvature kappa is magnitude of the second derivative. So this is curvature. You see here in this case, the normal really changes fast, right? Normal vector field, how quickly it pulls itself away, or how quickly it changes. It's the rate of change of the normal you can think of. Now binormal tells us something about the twist of the curve. Remember, relates to torsion. Binormal relates to torsion of the curve, and this was curvature relates to both n and the first derivative of the that tangent, right? Or t prime, curvature related to that. Now torsion, remember, torsion tau, this was equal to this time the how much the binormal, the twist. Maybe I can just talk about this. Remember, the tangents and the normal, they define a plane, right? Two vectors, they define a plane. And binormal was actually the normal of that plane. We call that oscillating plane. So this is B, sorry, B vector. And how quickly when a curve is twisting, remember, right? B changes, binormal changes a lot. So this is a measure of that. So this tells us how much the curve twists this time. Sorry, how much the curve twists. So it's like really, now you guys, I think, I hope, are in a position to characterize curves, this structure, important mathematical geometric entity curve. We can define a curve by how much it bends, like we're showing, and how much it twists. And that was also tying to, remember, to this fundamental theorem, first, I think, fundamental theorem of local theory of curves. Something, the name is something like this. I can't recall now, but please check. And it was saying for a regular curve, given for a regular curve, this is again very roughly as I recall, given the curvature function all along the curve with all parameters tau s and the torsion function for a regular curve, then this defines the curve. This defines the curve uniquely up to a rigid motion. I think you all understand now what this means. Up to a rigid motion means take a curve, rotate it. Okay, let me try to draw a curve so that I can rotate it now. Now let's rotate this guy. For instance, it's rotated, right? Rigid motion. If this kappa, tau are given and they are the same, I mean, just take a curve, okay, calculate its kappa and tau, just do a rigid motion on the curve. These guys stay the same. That means that, right? Because it's still the same curve, but only rotated and translated in 3D to some place. It makes sense, right? Rigid means you guys now know this very well. This SE3, for instance, or SE2, special Euclidean group SE3 or SE2. These guys don't really deform the curve, but I mean, this type of motion, rotation and translation. So our curvature and torsion functions don't change. It would be the same curve. I think this really nicely summarizes the important concepts in differential geometry of curves. Of course, there may be other details. I referred you, I think, to Doccarmo book. Where is that reference? Doccarmo, guys, please, for those interested, study. You can always go to our first reference that comes to mind, the reference book. That comes to mind in, I think, differential geometry is Doccarmo, great mathematician. Thanks to him, I really like his books. Also, the next step from there is Riemannian. Here also has a Riemannian geometry book. I think this summarizes what we did last time, and we can now continue with differential geometry of surfaces. Okay? Any questions from there? I hope you guys also like these topics like I like. I really enjoy. I mean, you enjoy them too, and at least even sparking an interest in you is, I think, enough for me. It's okay. Typhoon has been waiting. I just saw. Admitted anyone else? Okay. So now differential geometry. Let's do a quick introduction. Of course, this is much more involved. Surfaces, again, my reference was Doccarmo book here. I created these notes actually by looking at Doccarmo book. Now, like we defined curves in 2D, remember, I'll make an analogy like, for instance, curves in 2D or 3D, doesn't matter, 2D or 3D. Remember, from an interval to, for instance, this was, let's say, 0, 1 to R2 or R3, okay? We were saying a regular curve, the tangent should not be, or tangent vector should be defined for all P, okay? And also here, I should say C of P was, let's say 2D, XP, YP, and these X and Y should also be our continuous functions on, let's maybe, these details are all in Karma, but the Karma functions on the interval I. Now, you see here the tangent, it's a vector along this 1D manifold, like a string, right? It's a string. Now for a surface, we start talking about patches, right? Some tangent planes. So we have a patch. So a surface here, curves were 1D manifolds. Now surfaces are 2D manifolds. Okay, so a surface is a 2D structure, meaning I now will need two parameters to parameterize my surface, because now you see I have a patch. So I need UV typically. So a surface is to be parameterized by these two parameters. A patch is a piece of a surface, okay, of a surface. And its definition now, guys, is a surface also is a map. A curve was a map. This was a map, remember. From the interval I to R2 or R3 to a space curve, right? And now a surface is also a map, from this patch, okay? So again, I will have this time two intervals exactly. So because I have UV cross, so 0, 1, define two intervals for these two parameters, okay? So it will be really like SUV. This is now from R2 in a way. So a curve is a map from this interval I cross I. So it's actually from a patch to, it's a map from a patch to R3. Okay, this defines actually now my here parameterization is SUV mapping. SUV is really a mapping in display. XUV, YUV, ZUV. Again, of course, these X, Y, Z are continuous functions on this UV patch. Okay, this is a parameterization. This is called a parameterization of your surface S. Okay, I mean this one. I think at this point we should define a regular surface. Yeah, but to do that we need to go to the derivatives. Now we will be going there. Okay, so until here we are all good, I think, right? Now let's, I mean, we are just defining, actually making a definition of a surface. Now let me draw a surface here. Okay. This is, let's say, a surface S. I'm at a point P here. Okay. Here, what's important will be for us to be able to define something called a tangent plane. Okay. And we will be looking for tangent vectors, this time 2 tangent vectors to define that plane. I need, right, 2 basis vectors there, tangent vectors. But actually, maybe I should, before going there, let me actually, guys, start from the parameterization. Let's do this. So I have, guys, this patch or 2D. It's, you know, S is a mapping from R2 to R3, right? So U, V, okay. So let's define a patch here. It can be arbitrary shape, a patch U, a region U in 2D, okay? And there is a point UV here. Now I'll define, let's draw this nicely. Sorry, I deleted the other one. Okay, so you see, I'm drawing a 3D space because surface is embedded. You see, embedding is 3D space. Sometimes I ask these to students, for instance, what is the dimension of this object you're seeing? It's like a, I mean, everybody is like, hey, that's a 3D object, but the intrinsic dimension, actually, this is a 2D surface, right? Because there is a patch, right? Now we will be defining the tangent plane, actually, is important, and we can cover this surface or parameterize this surface by combination union of all those patches. Okay, and you see now this is one dimension higher in terms of manifolds than the curve. Curve was a one-dimensional string. Always remember it as a string, 1D, right? İp in Turkey. Now we also remember this guy as a patch of pieces, right? Patches, planes, sorry, 2D patches covering my surface. So in 3D, that's why it's a 2D manifold. Okay, so now we said S is a mapping. Okay, let me draw a surface here. Okay, so S is, you see, this is a patch of, I mean, it's in 3D, a surface, sorry. I mean, it's a surface, S. So S is a mapping from this UV to a point P here, let's say. Okay, so this is my S mapping, the one we defined. Okay, so it's really like S is from this 2D U space or patch to R3. Okay, so now my point P, okay. So we said now S is a mapping from this 2D patch or 2D UV parameterized piece of 2D plane, actually, right? A region, 2D region. We are mapping to, so this is really S of UV. So let's say this is that point P SUV, and that's really equal to, actually, that's equal to XUV, right? Because we are in 3D now, and ZUV at that point P. Okay, so now we define here something called a tangent plane, and we will be able to do that by, now because I have SUV, S of UV, right, the parameterized surface, I can take its derivatives along these two UV axes. So I will have, so let's draw the tangent plane. So I have, so let's maybe plot it in this way. I think you all can visualize such a tangent plane, right? So it's really like, imagine a point here and just imagine a 2D, of course, smaller plane here on top of it. This is a ruler, but that's a tangent plane, right? At that point, it's tangent to the surface. And how it is defined or parameterized? By these guys two. So let's maybe make this P, middle P. So maybe let's just say, okay, I can really, I mean, it doesn't have to go on here, but let's say maybe SU, this is on the plane, by the way, SV. Okay, so it has two, I need to define two tangent vectors, and I can go with SU and SV vectors. These are vectors, of course, right? These are tangent vectors. Of course, there are infinitely many arbitrary tangent vectors on that plane, but according to my parameterization, this SUV parameterization, I can find two arbitrary tangent vectors, right? Once I have a tangent plane, great, now I can look at the normal of that plane, and I can define the normal to my surface. And that's the other nice thing about the tangent plane. Now we can start talking about normal to the surface, right? And then normal, again, I bring my cup, is, I think all of you can imagine, this will be something, it will be a map, we will call it a Gauss map. That guy will be also changing over the surface, and the way it changes will give us the curvature, but curvature on the surface is much different because we have now infinitely many tangent directions. We will define the curvature along those different directions and look at max and mean curvature. It's not as easy as in 2D, okay? So now we can also again say, maybe recall this arc length or this differential arc length into the curves CP dP, because I want to define something called the differential area. This was differential arc length. I mean, this is really by taking derivative of the S of P, right? We did that here. Where is my? We defined S of P from here. ds is really, just look at there, C of, here this was P, right? Sorry guys, this is P, of course, 0 to P, because here my parameter you see is P. It was really CP, C sub P or C prime dP from here, okay? I mean, these are from calculus, right? From the fundamental theorem of calculus for this derivative, we can write this down. So ds, differential arc length, is speed of the curve, right? The magnitude of the tangent times the, actually, again, that infinitesimal parameter dp, decimal derivative of the parameter. So now we do the same. This was differential arc length. Now we will also define differential area. So we're trying to come up with entities, geometric entities, okay, definitions for defining. We will also do that, like lengths on a surface, because these are curved surfaces now, right? It's not a Euclidean space. We will now look at something called first fundamental theorem, which will, or first fundamental form, which will give us this, what is called a Riemannian metric. So that metric on a curved space, it won't be identity. On a Euclidean space, that's identity. So differential area, first of all, will be given by, you see these SU, SV are important. It will be SU cross SV magnitude. And that SU cross SV actually, guys, gives me normal, right? My normal, first maybe, okay, du dv. I need also du dv. Sorry, let's maybe, before that, let's first define the normal. So from here, I see that normal should be in the direction of SU cross SV, right? But I will also normalize it by, let's write it here, the normal curve is SU cross the cross product of the two tangent vectors, obviously, right? That's normal to those guys, but also get the unit normal. To get the unit normal, I have to then really normalize by the magnitude of the numerator, right? That's it actually. This is at point P. Normal to the surface at point P. Now we can write maybe the differential area. Here this was left. Now dA will be SU cross SV du dv. Because if you want to calculate the area, we will be using this. It's coming up soon. And P. Now, in the definition of the surface, we should now define a regular surface. Remember here we said a surface is a map from this UV region in R2, UV, wherever UV are spanning U. Here it's I, this I cross I. That's really in a region R. Now it's going to R3, but for a regular surface, the definition, maybe I can go here. So regular surface, I want to define what is like we did in a regular curve, remember. Regular curve, tangent should be defined. Similarly here, actually, for a regular surface, I want this one. First of all, SUV is differentiable because I want to be able to calculate my tangent vectors, okay? Then also these XUV, YUV, ZUV, right? My embedding in 3D have continuous, I mean, it's equivalent, right? This is really SUV actually. Have continuous partial derivatives, I mean, equivalently actually, it's differentiable derivatives and SU, the del S by del U is not zero, del S by del V is not zero, this is del S by del U, V is not zero, and then also SU cross product SV should not be the zero vector, okay? Should not be zero because this is my normal, right? So I want my tangent vectors and normal vector to be defined. So that is a regular surface S. Definition of a regular surface S. Okay, so this is important. Now let's again define SU, SV are tangent vectors, then we can say any linear combination of these two guys, just take a linear combination. These guys are also tangent vectors and they will parameterize this 2D map. So on the surface, SU, SV, okay. And I mean, it's a tangent plane, they parameterize this SU, SV, actually, I should say are basis vectors for, we can take them as our basis vectors, those tangent vectors as the basis vectors for the tangent plane. So they define the tangent plane, but actually I shouldn't probably say they define. I can take arbitrary tangent vectors on this, right? I have infinitely many, I can say, can have arbitrarily many tangent vectors, right? tangent vectors on this plane. But all SU, SV lie on this tangent plane. So taking two of them which are orthogonal, at least which are not zero and whose cross product is not zero is enough. They define my tangent plane. This is tangent plane. Tangent vectors on the tangent plane, let's say. This is important. So our tangent vectors on the tangent plane to the surface S and at point P. At point P, this is important, that will change, right? I mean, as I move on this surface, for instance, I come here, another point Q, let's say, now my tangent vector will, of course, be changing. It's a curved surface, right? Curved surface, of course. So tangent plane, we call this tangent plane typically TPS. This would be TQS, okay? TPS, tangent plane at point P on the surface. I hope these are clear. Very geometric stuff. I mean, it's really, I think, nice to visualize, easy to visualize. Okay, I had a formal definition of the tangent plane. Let's write it just for our notes' sake. Definition, I said tangent vectors SU, SV form a vector space, vector space of dimension 2, as we expected, because this is a 2D manifold, called the tangent plane. It's really a plane then, right? 2D, called the tangent plane at P, and like we named it, it's T sub PS, and then SU at point P, of course. Somehow we should show this actually. SV, these two vectors at point P are basis vectors. They can really act as basis vectors of T of P. I mean TP of S, sorry. All right, this is the tangent plane. So now, after defining tangent plane, we want to define the first fundamental form, which is the Riemannian metric. So maybe let's define that, and after that, give a break. Okay, so the first fundamental form. The first fundamental form. Okay, this is also sometimes called Riemannian metric. Riemannian metric. Okay. Now, we will this time for the first fundamental form, we start with a curve on the plane, okay? I mean, a 1D manifold. We will map that curve from the 2D region onto the curve. We start by that. Then we will measure length of that curve on the surface. That's the point. So we will start by, guys, so let me define again our 2D region patch. Remember, always keep in your mind when we talk about a 2D manifold, there is this 2D parameterization. So now in this space, I mean, I'm drawing just a patch for us to remember. Let's draw a curve, alpha of t. Now you guys know curves from last week, from last time. Now we will map that alpha of t. It's a curve, 1D manifold, okay? Now we map that guy onto the surface. So let's draw a surface here. An arbitrary surface. Okay, it's S. So now guys, let's map this curve, we said. Let's map this onto Maybe let's not use, let's use red here actually and do the mapping like this. This is really a mapping through, like, use the parameterization, right? S is really a mapping actually, R2 to R3. So I can take that alpha of t, map it onto the surface. So that would be S of alpha of t, right? This curve now on the surface is S of alpha of t. It's carried onto the surface. It's curved there. Let's call it, I mean, equivalently, it's a C of t, right? There is just one parameter, let's say. I know because that is parameterized by some one parameter t. Okay. Now C of t, this C of t, which is S alpha of t, this will help us to define the first fundamental form on the surface. That's why we're doing this all of a sudden. This is my curve on the surface. So actually it's also equivalent to S of U of t coming from that patch, right? B of t. Now we'll take, because we know how to do this actually from last time, we'll take derivative. We'll look at the derivative of C, this curve on the surface, C of t. Now take the derivative, C prime, okay, is S sub U, because, okay, actually maybe let's take the derivative from here. S sub U, I can do this, that's my tangent vector, UT, plus S sub V, VT, right? This is now helping me because I want to look at again the magnitude of this thing, the speed. So let's do that. Let's for ease look at first the square of the magnitude, right? Because that's really the inner product without the square root. Then I would have, let's bring it here. Let's bring C prime T. I mean, let's do this. Remember, this would be really inner product C prime T, right? This is the inner product. I'm now writing that guy. Let's bring my expression S sub U UT plus S sub V VT. Its inner product with itself, UT plus SV VT. Okay. Now this is an inner product in R3. Let's do this inner product. Okay. We'll try to see now how that Euclidean inner product is changing on a curved surface locally. At each point, we will change that inner product metric. Until now, you have seen this as probably always as in Euclidean space, that was identity. Now it's gonna change. Now let's do this. That's why I'm hoping it's exciting for you. So we were here at this point. Now I'm doing opening this up, guys, this inner product. So I will have an SU dot SU UT squared. So let's write this SU dot SU UT squared plus 2 SU dot SV. You see, I have tangent vectors UT VT plus SV dot SV VT squared. You see now I have these terms. Normally, if it was a Euclidean space, we will now compare actually. We would have E equals 1 UT squared. SU dot SV would have been 0. We name these. Now we give these new variable names, G. Okay. Now this E, F, G are my first fundamental form of the surface. They change at every point on the surface. First fundamental form coefficients. We'll write a matrix actually, 2 by 2 matrix. Coefficients, okay? E, F, G. So let's now rewrite this magnitude squared, C prime T squared, okay? So it will be equal to, I'm just rewriting UT, VT. Here, for what is important for me is in this matrix, SU dot SU, these are important, SU dot SV, is, I mean, it's the same, of course, and SV.SV. This is the first fundamental form, this matrix here in the middle. If that was identity, I would be in the Euclidean space, and I would, my C prime T squared would be just UTVT dot product with UTVT. But for a curved surface, that is not identity. That doesn't have to be identity. It could also still be equivalent to a Euclidean surface, but it's fine. Euclidean space, we will see. So this is a quadratic form. You see now this matrix is called sometimes short y because it's first fundamental form in Roman numeral I, guys, at point P. So it's really first fundamental form. Okay, IP at P, of course. You see, that's the idea. Over the curve surface, this changes, and it is a IP, guys. It's maybe, let's write matrices with double bars underneath. It's a positive definite, right? Because SU is really its inner product with itself, SU squared, SV.SV squared. You can find it, it's positive definite and symmetric matrix. Okay, so IP is really, this first fundamental form is really from our defined coefficients, EFG. Okay, and now where do I use this? For instance, I can use this in calculating lengths and areas over my surface. So let's do it. For instance, this is now, let's say I am able to calculate this. Now let's see, or until here, I know it's a lot of material, but really even getting exposed to this is good. Don't worry. But of course, you have to really think about this on your own, study these on your own. But after this lecture, I believe you will be much more confident in, for instance, opening up the Carmo differential geometry of curves and surfaces book and go over most of the chapters. Of course, there will be some advanced chapters, but first 5-6 chapters you should be able to read. That's my goal, actually. Yes. So we just defined the first fundamental form where E was the first tangent vector dot itself, F was the SU dot SV, right? And G was SV, the other tangent vectors. These were my fundamental form coefficients, first fundamental form coefficients. It's really, this first fundamental form plays an important role in characterizing surfaces. Okay, then for instance, I want to, let's say, measure lengths over a surface. Okay, or I want to calculate area over a surface. First fundamental form is what we resort to. So maybe let's show on a curved surface. So here, this intuition is important, guys. Let's write this. On a curved surface, right? I mean, we're talking about these not flat geometry. So contrary to a flat surface. I mean, we are used to working with flat surfaces, right? Euclidean space. The inner product, okay, induced by the Riemannian metric. It's actually by this EFG, induced by the Riemannian metric. Okay, this guy. I mean, the importance, that's why I put it in quotes. On the tangent space at every point. Every point changes. This is important, guys. Riemannian metric changes as we move, as the point moves on the surface, as the point moves on the surface, let's say. Okay. So, for instance, okay, let's do this length calculation. Okay, so again, I draw a surface here. Okay, S. So let's just maybe, it's a curved surface. So for instance, let's say I have a point P, okay, and I'm here at some, okay, so it's a P is S of, right? It's a mapping from this UV, remember? And actually it was the curve that was parameterized. Let's say in this 2D region, it was T0 to T1. Now it's mapped onto this curved surface. VT0, S of those guys, to a Q on another point on my surface. That's U of T1, V of T1. Now I want to, this is my curve C of T. Now you guys know curves well. And I want to look at the length. Okay, here I want to calculate my length of this curve on my surface. And let's say LPQ. How do I calculate? Calculate this length, okay? So calculate the length. For instance, let's say calculate the length here, LPQ, LPQ, okay? That guy will be, now this quadratic form will help me. This E or IP, first fundamental form was, remember, IP matrix formed by this EFFG. LPQ, it's T0 to T1. Remember, I can calculate the length, right? It's the arc length from between those two parameters. However, this inner product now changes, okay? It's E UT squared, as we've actually already shown, 2F UT VT plus G VT squared, and I need, this was, remember, C of C prime T squared, right? I have a DT here. I hope it's visible there. Okay, and you see here, these guys are giving me the local metric, actually, the changing metric, right? Over that curved, over the curve actually on the surface. So it's a curved surface that we are following, right? Over this curve, and we're here calculating the length. So similarly, right, just a sec. Yaşlılar. Okay. So, all right. So this is how I would calculate length on the surface, joining 2 points on the surface, P and Q. Okay. So you see, first fundamental form helps me measure that length. Now, similarly, the area, let's say, area element, we were showing it. Similarly, to calculate area, let's say, similarly, to calculate area of a patch, given area, dA, we said, is SU cross SV, du dV. I think you guys recall this, right? Any parallelogram, this is again calculus, SU, SV, right? The area was given by exactly by this magnitude of this cross product. If you recall this from, I think, your calculus, right? That's why actually this is valid. So you see now on the surface, we can calculate the area. Let's say, for instance, I can go to a region. It's a curved surface, right? So I can go, and here, let's say this is my region R, and I want to calculate its area. This time, guys, let's bring it here. I will do this over that region. I want to integrate dA. Okay. So now I can, by the way, this guy can be written as, we can look at this. I think it's in this way. Eg minus f square, again, in terms of the determinant of the first fundamental form. I think I had a derivation for this somewhere. Let's see, guys. Okay, I used Lagrange's identity to show this equivalence. We can, maybe for your notes, I can note this. Note, guys, this is it. A cross B squared. This is Lagrange's identity. To show that actually Lagrange's identity. I mean, you don't have to memorize these. I'm also checking my notes. A square B square, but it's good to know, minus A dot B squared. This is Lagrange's identity. Now I think because this was SU cross SV, right? I will do the math here. This will be SU dot SU, you see, times, okay, let's do it in this way. SV dot SV, the inner products, minus SU dot SV squared, right? And exactly, it is proved now. This area, this was, remember, the area element, because this is the E, the first fundamental form coefficient E, this is F, and this is, sorry, that is G. Of course, this is the other guy, SV, and this is F squared. That's why you see I have actually area. So area of a bounded region. So if you want to do an area calculation, you see that's why these things are important. Calculation of lengths, area. To do these, to be able to do these on also abstract spaces, curved spaces. Here, it's not that abstract. We can talk about really 2D manifolds, these surfaces. You see, I can calculate now an area on here, can calculate length of a surface, but we can also generalize or extend these ideas, concepts to n dimensions and curved spaces in n dimensions. It's not the n-dimensional Euclidean space. Those arbitrary n-dimensional abstract spaces in embedded in, for instance, n dimensions, Rn. So area of a bounded region R on the surface S. We know how to calculate it. We just showed Eg minus F square. You see the coefficients of the, that's the area actually. The coefficients of the first fundamental form help us actually. Okay, this is an important, guys, quantity that is used in differential geometry. I mean, this first fundamental form. It's important to study and know. So now I think at this point we can look at a few surface examples. Okay. So for instance, I can just talk about an example, a plane. Let's start with the most simple surface, which is a plane, a planar surface. Of course, embedded, it can still be embedded in 3D. Let's say it's really embedded in X, Y, Z, okay, a plane. It's a planar surface or just a plane. Now, what is its parameterization? I can now you guys can recognize this. I can say U, just use UV and a constant. Just cut this Z. So maybe I should have done shown it the other way around. So let's maybe show it in this way. This would be because more relevant the way I'm showing it, right? X, Y, Z, a constant in the Z and UV are in the same axis as X, Y. This is clear, right? This is a plane parameterization in 3D, in R3. A plane, a very easy, a plane parameterization, a straightforward surface parameterization, you see. Now I can, for instance, I'm asking you question, calculate the first fundamental form coefficients. First fundamental form coefficients. Okay, so you should calculate E, F, and G. So these are really E, F, G. What are they? You need SU and SV, S sub U and S sub V, right? So this is del S by del U for each of the arguments in R3. So it will be really 1, 0, 0, 1, 0, 0, and 0, 0, 1, 0, right? These two vectors are my actually two tangent vectors. It's already itself actually. So, and you can just find E was SU dot SU, which is really 1. F is SU dot SV, which is 0. G is SV dot SV again, which is 1. Okay. So for instance, another example, I mean, guys, this is, by the way, a Euclidean plane, right? You see the inner product or the first fundamental form reduces to the identity matrix, right? Identity 2 by 2, identity matrix. It's not a curved surface. But one interesting thing is this first fundamental form does not really characterize a surface. I'll give you another surface example. Now look at this surface. SUV. What is this surface? My first question to you is, can you guys sign U and V? Can you guys just imagine in your mind? Let me again draw these X, Y, Z for you. I'm asking you, what is this surface? Can you, in your mind, just in U, go over cosine and sine in the plane? What is that? That's a circle, right? So that would be a circle. And then in the third dimension, you go up. So it's a cylinder actually, cylindrical surface. Okay? So I hope you can see, all of you can see this. This is a parameterization, right, of a cylindrical surface, right? So what are the tangent vectors? So SU, S sub U is, of course, just do the math here, minus sine U, cosine U, 0. Now SV is actually 0, 0, 1. From here, E is actually, just do the math. SU dot SU, it's the magnitude of the first tangent, it's 1 vector. F is 0 and G is 1. Guys, check out these two, compare these two fundamental forms. This is, I think, very interesting. What are E, F, and G? These were also E, F, and G. Look at these here. Compare. They are the same, right? So actually, a cylinder, you see, has the same first fundamental form as the plane. Okay. So in terms of curve lengths, areas, and in terms of the Riemannian metric, because think of a cylinder, you can open it up, unroll it, it's a plane, right? So locally, it looks like a plane, but of course there is curvature. We will talk about the second, that's why we need the second fundamental form to characterize a surface, like we did in the fundamental theorem of local theory of curves. There is a fundamental theorem of local theory of surfaces, which says we need first and second fundamental form to characterize a surface, again up to a rigid motion. That will be similar. There we needed, in the curves, we needed a curvature and torsion. Now we will need first fundamental form and second fundamental form. You see, the two, we should say, plane and cylinder have the same first fundamental form, right? So we should say first fundamental form does not characterize to form does not characterize a surface itself. Okay, I mean itself only does not. Okay, then let's look at maybe other examples. Does not characterize, let's say. What else maybe I can talk about? A sphere maybe. Okay, well, let's do that. For instance, sphere. I mean, of course, it will have, I mean, it's a sphere, right? In R3, let's say, I mean, I have UV, but you see it's a 2D manifold. Typically, remember, we show or just name the parameters as theta phi. So, for instance, a typical parameterization, cosine phi, sine theta, sine phi, right? And cosine phi, for instance. This is a parameterization of a sphere. Now, I think you guys can see the 2D manifold. It has two parameters, theta phi. I would need S sub theta and S sub phi. You guys can just go and calculate these. I will write the results. I already have in my notes. E is calculated as 1. I mean, these will be, E will be really S theta dot S theta. F is 0, which was S theta dot S phi. G is sine square theta. You see, this is not Euclidean. You see, my inner product has now S phi a non-unity form here, like non-identity. My fundamental form, first fundamental form is this, right? It is, so let's write maybe from here, my first fundamental form at each point. Of course, that theta changes at each point, so my I, the first fundamental form will be different, okay? This was SV dot SV. What else? Trying to see. Okay, I can also similarly talk about an ellipsoid. For instance, ellipsoid SUV. Okay, this time I just said UV, but I mean here I could have said UV too, right? UV, sine U, cos V, etc. A sine U, cosine V, B sine U, sine V. This is now you see A and B are different from the sphere. C cosine U. I mean, we could just use theta phi here as well. Here, actually, I should have shown probably the range of theta and phi there too. This is U. Let's do that for the sphere as well. 2 pi, one of them runs from 0 to pi, the other runs from 0 to 2 pi, remember. And A, B, C are not 0. Here also then I should have theta between 0 to pi, phi between 0 to 2 pi, right? And there A, B, C were 1, of course. A, B, C were all 1. Sphere for a sphere, but now for an ellipsoid, you see, that would be a shape. Right? I mean, I hope you can all visualize these things in your mind. That's a surface, ellipsoid surface. Let's see. Actually, I can show also the implicit representation of this guy. Let's see that. I think I showed this in a slide. Let's see. This can be written in another way. Ellipsoids. So guys, there is also implicit surface representation. I can also talk about S can be defined as XYZ such that a function, this is an implicit surface representation, but you can always bring it to again a parameterized surface, fxyz equals c, okay? And that fxyz equals c for an ellipse, for instance, for an ellipsoid is this guy. Ellipsoid is x squared over 8, for instance, y squared over v plus z squared. I think this is something that you guys are used to from before, right? So I want to recall maybe for you how I can come up with the maybe SUV for this one. So I would say this is in R3, by the way, right? Guys, it's a constant. C is a constant in R, right? It's like a level curve. Remember, this is an implicit surface representation. From here, I can just say my SUV is F inverse C, okay? And I can still map it to, of course, XUV, YUV, CUV, okay? Or we talk about, for instance, an implicit parameterization. I can say X, Y, for instance, e.g. This is called a graph parameterization of a surface. Maybe you guys have talked about this before in some other calculus course. X, Y, F, X, Y. Okay, I'm talking about a Z here. Let me see here. So I have this somewhere, guys. Now I wanted to say fxy. This is another thing, by the way. Okay, I shouldn't probably a graph parameterization. This is z is equal to f of xy. This is also another parameterization. You can talk about, for instance, okay, let me note this. For instance, an image function. If you have been working on images, an image function, we can write it as a surface. Can be written in a surface parameterization as a graph function, can be written as a surface. So that would be really like what I wrote here, x, y, and then the third parameter is the ixy, remember. So then f of xy, so this is really the surface, x, y, I of xy. Then you can, because talk about, you view the image as a curved surface with its intensity being this third embedding, the z, okay? And then you can talk about its first fundamental form. Now we will talk about its second fundamental form, and try to use those, for instance, to make measurements over the image graph, or to make, for instance, measure things like curvature and things like that. So for instance, for this one, maybe I can say, for instance, I can talk about as the normal vectors. I was talking about this parameterization as in my notes, and I said, let me see, x of t, y of t. Okay, I was talking about a curve here. So t, y, t tangent vector to the surface. So please check let's check this actually, because I went to a single parameter here. Maybe I shouldn't really confuse you at this point with this. Yeah, let's not digress actually. This was an extra thing that I should probably not digressing to. Okay. So my point here was, where did we come to this? I was trying to say, guys, ellipsoid, this is a typical parameterization. Now you guys can find, so let's continue, S sub U, S sub V, these you can calculate, and from there you can find its Riemannian metric, right? EFG, I mean this EFG, to make your measurements. The reason I went to all this digression was, I can also, I thought you may be used to this implicit representation of an ellipsoid here, given here. From there also you can tie to this explicit parameterization. So this is implicit parameterization versus this was my point actually here, explicit parameterization.